Okay. The next speaker is Son Han, who's an assistant professor at the Department of Electrical Engineering and Computer Science at MIT. Son, please take it away.
All right. Good afternoon, everyone. I'm very glad here to present our recent work on fast and efficient AI inference. So our focus is on improving the computation efficiency, engineering efficiency, and data efficiency for modern deep learning. So like Nima mentioned, modern deep learning requires a lot of data, a lot of computation, and many engineers to design smart algorithms. So we hope to reduce the resource needed by all these three pillars by compressing the resource. Okay, so we can use less amount of training data to produce equally good models. For example, our recent neural reps paper called Deep Augment. By data augmentation, we can train GANs with only 20% of the training data, while equally making even better FID results. And we can use only 100 images to train very good GANs compared with like style GAN 2 that used to require 70,000 training images. Okay, so less data and less computation. We want to enable model compression so that the neural networks require a much less number of parameters and also fewer bits for efficient inference. For example, our neural reps 20 paper called MCUNet, we enable deploying deep neural nets on microcontrollers that has only 1 megabyte of flash. Imagine what you can do with only 1 megabyte of flash. So we can achieve really good accuracy with such microcontrollers. So we can achieve more than 60% top-line accuracy on ImageNet 1000 classification with 1 megabyte of flash. And we can achieve more than 70% top-line accuracy with 2 megabytes of flash. Okay, so designing neural nets with that require less computation. And finally, how to enable AutoML techniques and neural architecture search techniques that can automatically design those efficient models without many human efforts. So our work called Once for All network, we can design neural nets and amortize the design cost across many hardware devices like CPUs, DSPs, and GPUs, and which received the first place in many low-power computer vision challenges across all the tracks, including the CPU track, DSP track, and also the FPGA track. Okay.
Song, I think your slides are not advancing.
I didn't advance my slide.
Okay, great.
So let's start with the background knowledge. Pruning and compression, which was from my PhD thesis. So pruning can basically reduce the amount of parameters by about 10 times for FC layers and 3x for the conv layers. And together with quantization, we can further compress deep neural nets. So altogether, it's called deep compression, where we can reduce the model size of AlexNet by 35 times, at that time, and VGG for 49 times. And later, like ResNet and MobileNet, they can all be compressed. So which has recently attracted a lot of attention. So if you search network pruning on Google, the number of publications shown is, so started from 1990, from optimal brain damage all the way to 2015 from my paper, Learning Both Ways and Connections for Efficient Neural Nets. And then it suddenly exploded. So the attention suddenly increased so much since 2015, where we can combine this pruning and sparsity together with the hardware and to efficiently accelerate deep neural networks to bridge the gap between theory and the practice. Data, a lot of data, a lot of computation, many engineers, now less data, less computation, fewer engineers. So model compression, pruning techniques, and then the amount of publications for pruning and sparsity started 1990 and all the way to 2015, suddenly increased a lot, which impacted the NVIDIA GPU. Now support 2 to 4 sparsity. Okay, so 2x speed up. So these are some of my previous papers and recent papers that talk about how to accelerate and support sparse neural network inference. Pretty good, awesome speed up results. So recently, I find model compression itself is not enough. Okay, so from cloud AI on GPUs to mobile AI on the phones to tiny AI on microcontrollers, there's a huge gap between the amount of computational resource. So from many gigabytes of RAM to only like 100 kilobyte of memory. Okay, and the computation is only several million flops per second. So lots of pretty big gap. So we propose this thing called MCUNet, tiny deep learning on IoT devices for microcontrollers, micro MCUs. So MCU, again, here we have 50,000 times smaller amount of memory compared with desktop GPU. So here on the right-hand side, we proposed the inference engine called a tiny engine together with a neural architecture search method targeting microcontrollers called tiny NAS. And we co-design the system and also the algorithm to design the best fitting neural network architectures together with the compiler as well as the runtime. So we co-design the neural architecture with the compiler and runtime, and we can achieve significant speed up compared with traditional methods. So you compared with the yellow one is the TensorFlow Lite, and these two out-of-memory ones are TVM and also TVM tuned. They're completely out of memory under tight constraint for these three benchmarks on ImageNet. And the blue one is the CMCs provided by ARM. So compared with which is the so far the best optimized neural network inference engine on microcontrollers. But even compared with ARM's CMCs, we can achieve 1.5 to 1.6 times speed up compared with the hand optimized CMCs. And accuracy-wise, we improved the baseline accuracy from only less than 40% top-line accuracy. Together with, if we add the tiny engine system level optimization, the accuracy can improve to 43.8%. And if we apply our tiny NAS, the accuracy improved to 55%. If we apply both the tiny engine and tiny NAS, we can improve the accuracy to 60% top line on ImageNet with only 1 megabyte of flash and 256 kilobytes of SRAM, which is a pretty tiny amount of hardware resources. So in comparison, the BLVC AlexNet is only 57% top line accuracy. Another demand that we have is how can we automate the process of efficient neural architecture design without human to tune the number of channels, number of layers, number of kernel, the resolution, connectivity, etc. So it used to require lots of human expertise. Now we want to have a push the button solution that can automatically design efficient, compact, and fast neural architectures given a design constraint, also called neural architecture search. However, traditionally this comes at the cost of big ML, where neural architecture search is really expensive to train and to search. Okay, so although the provided model is efficient, but the training and search process is really expensive. So for example, here, MIT News, MIT Technology Review said training a single AI model can emit as much carbon as 5 cars in their lifetimes. So deep learning has an outsized environmental impact. So a pretty big problem. So this is the from the original paper in ACL 19, where a round trip from New York to San Francisco for one passenger is taking roughly 2,000 pounds of CO2 emission. A US car, including fuel, will average one lifetime 126,000 pounds of CO2. And doing neural architecture search on transformer, okay? Transformer with neural architecture search is taking 600,000 pounds of CO2, which is like 5 times compared with the US car average one lifetime. With our approach, we can reduce the cost by 4 orders of magnitude. We published in ACL 20. And the key idea for this huge saving is this method called once-for-all network. Okay, so we train one network to specialize it for efficient deployment for many different scenarios. So the marginal cost is close to zero. Okay, so we can design just one single once-for-all network. And for GPU, we can sample a larger subnetwork. For a mobile phone, we can sample a smaller subnetwork. For a tiny microcontroller, we can sample an even smaller subnetwork. Okay, so all these subnetworks can be produced for free without any retraining, since the once-for-all network guarantees that for different subnetworks, the accuracy is well maintained without hurting each other. Okay, and benchmarked and compared with a pool of popular networks, we are using a very small amount of computation. So the x-axis here is the amount of max, y-axis here is the accuracy. So we are on the top left corner. So compared with the Res 50 exception, Res Next 101, etc., much smaller amount of computation. And compared with other efficient models, including Dart, ShuffleNet, MobileNet V2, Proxyless NAS, MobileNet V3, EfficientNet, we are having a higher accuracy and lower flops. Not only flops, but also measured latency. OFA once-for-all network enables fast specialization on diverse hardware platforms, including the CPU, GPU, mobile phone, and also FPGAs. So the first row is the result on Samsung phone, Google phone, and LG phone. So this is the trade-off curve of latency and accuracy. So with similar accuracy, we can decrease the latency by a large margin on these platforms. And you can just use one model to specialize it for many different platforms. For example, on NVIDIA GPUs, we can reduce the latency from like 28 milliseconds to only less than roughly 12 milliseconds, okay, without any change in hardware and the library. Just by designing this compact and efficient model, we can achieve more than 2x speed up without sacrificing any of the accuracy. And also on Intel CPUs, we can achieve a much faster inference. Even the Xilinx FPGAs, so even on specialized hardware, we can improve the utilization by roughly 60 to 70% without losing any accuracy. For example, on the x-axis, we can improve the accuracy, but with an even shorter latency from a little bit more than 6 milliseconds to roughly 4 milliseconds. So here we have some demos. So this is super resolution without acceleration. Okay, so CARM model running 16 frames per second, turning a low resolution video into a high resolution video. Okay, you can see the world is moving pretty slowly because it requires pixel-wise processing, which is really computationally expensive. So after our acceleration with our efficient model, it moves much faster, okay? 41 frames per second without losing any of the accuracy. And the world is moving much faster. Here is another demo for GANs. So without our technique on GAN compression, the demo can run at only, let me actually share the whole screen so that you can see. Can you see the video in full screen mode?
Yes.
Yep.
Okay, good. So before compression, this is the frame rate. It's only running at 1.6 frames per second on a edge device, just a nano GPU, pretty slow. So turning a horse into a zebra, but again, it's pixel-wise prediction, so very computationally expensive. So with our smartly designed model after GAN compression, we can run much faster on 5.3 frames per second, which is 3 times faster. And also we apply our method to video recognition. So before compression, the conventional i3D model is running 164 milliseconds per video. top point accuracy is 41.6. Our method, we require only 17.4 milliseconds per video. And the top point accuracy even improved to 43.4% on the challenging something V1 dataset. 9 times speed up. And this is comparing the throughput. So measure on the GPU. Previously, it's running 6 videos per second. Now it can process 77 videos per second with even better accuracy. So 12.7 times higher throughput with our acceleration techniques. So same GPU, same hardware, same inference library. With our smartly designed model, we can run much faster. So we also want to talk about efficient training. So we want to scale up a large-scale distributed training. So we used the Summit supercomputer at Oak Ridge National Lab. So we are able to scale up. We find that the challenge point is we want to reduce the computation, not only reduce the computation, but also reduce the amount of networking bandwidth and for exchanging the gradient, and also reduce the disk bandwidth by reducing the amount of frames to access from the disk. So by applying our optimizations, we can do large-scale distributed training, scaling to 1,536 GPUs, and the task can complete from 49 hours and 15 minutes, more than 2 days, to only 14 minutes, only a cup of coffee. Okay, and the accuracy is well maintained, 74.1 versus 74.4.0. The theoretical speed up is 256 times, and the actual speed up is 211 times. And we can also dissect to understand what is happening in the video. For example, wiping the area, we can highlight spatially and also temporally the regions where we are wiping something. The 3rd frame, 5th frame, this region indicates that we are wiping something. Okay. All right, so we talk about computation efficiency. We also want to talk about data efficiency. So collecting data is very expensive. Labeling data is even more expensive. We want to enable efficient deep learning with less data. So this is an example generating faces. So the baseline using StyleGAN 2 needs 70,000 images. So if using less image, say 100 image, the produced image is very poor. Like using my image, only 100 images of me, the generated quality is really poor. But with our method called deep augmentation, we can train the same model with much fewer number of images, with only 100 images. But you can see that the quality of the generated image is actually pretty good and much better than the baseline. And the key idea is to apply differentiable augmentation at both the before the discriminator and also at the generator. Since the gradient has to pass to the generator, it has to be differentiable. And the second observation is that we need to apply the augmentation to both real and fake images. So as a result, we can train, for example, on CIFAR and CIFAR 100 with only 20% of the data. But you can see the inception score is still well maintained compared with the dashed line. Okay. Similarly for CIFAR 100, with only 20% of the data, we are still beyond the threshold of the baseline. So finally, let's switch gear to talk about efficient 3D deep learning, which is related to physics. So 3D deep learning has a wide range of applications, from scene segmentation to object detection to also particle discovery for high energy physics. Try to understand and label each particle what it is, and if this is an interesting collision. However, this is very computationally expensive, and as a result, you see this person playing VR, AR headsets has a whole backpack of computers, and the self-driving car for the LiDAR has a whole trunk of computers as well. And this is because 3D deep learning is very challenging, because for training, it requires 4 times slower for training due to more computation and sparsity, and also the inference cost. So the max per image is an order of magnitude larger than 2D images. Therefore, we applied the roadmap across 3 dimensions to produce efficient methods and inference library for 3D deep learning, including building efficient 3D building blocks and also 3D kernel optimization at the system level, and also 3D network design using neural architecture search.
So you have a couple of minutes left.
Yeah, so I'm not going to go to the details. So the high-level idea is having multiple branches covering specialized branches covering the large objects and also the small objects. Small objects like the person and cyclists and the trucks. We are using a specialized point-based branch to represent that, and we use sparse convolution to represent to model the adjacency and neighborhood information. So currently, this method ranks first on the 3D outdoor scene segmentation on the semantic kitty dataset, having a pretty good advantage. And also, it runs much faster compared with other baselines like point-CNN, DGCN, RSNet, 3D-UNet, etc. So more than, for example, compared with DGCN that requires 90 millisecond latency, our method requires only about less than 15 millisecond of latency. So more than 6 times faster, but with similar or even better accuracy. And this was applied to the driverless car at MIT. So detecting the cones on the left and also on the right. And also we can apply this technique to particle physics, where we collaborate with Phil and his team in high energy particle physics, where in a collision, we want to classify each point. So it's very similar for this task compared with our segmentation task. Basically, give the XYZ energy and time to classify what kind of type for each particle versus our. We also want to do a classification for each particle. So basically, that's segmentation. And we give a pretty high accuracy applying this technique, which used to be for our autonomous driving tasks, segmenting the trees and also the persons and pedestrians, etc. Now we want to differentiate the noise, HAD, EM, MIP, etc. And you see the diagonal. The accuracy is actually pretty good, especially for the noise. We can have very good accuracy filtering particles from noise. And this is showing some comparison of the ground truth on the right-hand side versus PVCN for both X and Y. So they are very similar. All right, so point voxel CNN is proving to be pretty promising for efficient 3D deep learning. It has been applied to MIT driverless team for their autonomous racing vehicles and have achieved pretty good speed up, ranging from 2.7 times to 6.9 times measured speed ups on many tasks, and a lot of memory saving as well. We think it's very promising for high energy particle physics as well. All right, in summary, today we talk about how to achieve improve the computation efficiency, engineer efficiency, and data efficiency, and toward more efficient deep learning inference with resource constraints. Okay, and all the work I talk about is open source. You're welcome to check out the GitHub, and also we have many resources on our website as well as our YouTube channel. Thank you.
Thanks a lot. A very nice talk, Song. Okay, we have time for a couple of questions.
Song, this is Tom Gibbs from NVIDIA. That was a very good talk. In fact, your dinner picture there at the end looks great. In fact, I can't wait till COVID is over so we could do something like that in the future. The question I had is when you were your last example with segmentation, I've seen recently some researchers applying a recurrent segmentation network. Is that something that you guys have explored?
No, we haven't explored that.
Yeah, it was actually applied to the collision operator in a plasma physics. But it was one of the example that and one that just came across in the last month. It's RESEG is the name of the network, and it combines a CNN with a recurrent, a couple of recurrent stages at the end. So it's a CNN in the beginning to kind of do some of the feature identification, and then a recurrent network to actually do the segmentation. It might be something that would be interesting in terms of some of the particle tracking. And since you'd kind of gone down that path, I'll,
Yeah, that sounds interesting. I probably want to check it out.
Yeah, your work there is very, the point voxel CNN is another very, is really interesting, but thanks.
Okay, thanks, Tom.
Anyone else?
Hi, Song. Nice talk. I just had a quick question. Where you talked about scaling on Summit supercomputer, I was just wondering, did you require any special kinds of optimizers to achieve fast convergence, or did you just rely on the traditional optimizers? Because it's one thing to achieve high efficiency, but then a lot of times we see like the convergence time degrades when you scale.
Yeah, we didn't change the optimizer. I believe our optimization is orthogonal to using the optimizer. We have a paper actually for all the details. Scaling distributed training, training kinetics in 15 minutes. You can search for that paper. So the optimization is not on the optimizer, but on how to save the communication bandwidth, the disk bandwidth, and also save the flops.
I see.
Okay, thanks a lot. So thanks again to Song for this amazing talk.